Hello everyone. My name is Mohammad Bashir, supporting mechanical team at DICOS. I work as senior mechanical engineer as material SME. In today's session, we will focus on additive manufacturing, which may also known as 3D printing technology. Even if you have never used a 3D printer or designed a part for additive manufacturing, you know that this represents a very important technology to manufacturing now and in the future. Here is the agenda for this webinar. During this webinar, we will look at the concepts, types, parameters, and application of additive manufacturing and rapid prototyping. Towards the end, I will share details about what services we offer in this area. We will start with manufacturing process. A manufacturing process is a process that takes a raw material, refine them into a product or a component through several operations. Manufacturing process result in something that you can touch and feel. As you all know, economic production of products with close tolerance, with neat shape and high accuracy is the challenging task for the manufacturing industry. So, two different approaches have evolved over the year for efficient and economical fabrication. They are subtractive manufacturing and additive manufacturing. In additive manufacturing approach, thin layer of semi-solid materials are deposited one over another to build a 3D object. On contrary to additive manufacturing approach, layer by layer materials can also removed from a solid blank to get a 3D object is called subtractive manufacturing. In additive manufacturing, layer by layer materials are added one over another to build a 3D shape. In this manufacturing concept, the volumetric density or weight of the component can be controlled during this process. In additive manufacturing process, minimum material wastage takes place during this, and even the waste material can be recycled. But in subtractive manufacturing, layer by layer materials are gradually removed from a solid blank to fabricate a 3D product. This concept can be applied to all materials, irrespective of its melting point, material properties, material characteristics, etc. In this process, material density cannot be controlled, and the process is associated with material wastage in the form of chips, scraps, vapors, etc. But any complex shapes can be easily fabricated using additive manufacturing, even structures containing fully closed and internal hollow parts. This process may be time consuming and costly based on product requirement, but can produce superior quality and desired properties. Rapid prototyping is another phrase that someone used to refer 3D printing technology. Initially, rapid prototyping was used exclusively to describe process for the rapid production of sample, models, or prototypes using generative process. Over time, the term rapid tooling and rapid manufacturing have also been combined to form the generic term rapid prototyping. Rapid tooling refers to the rapid production of tools using the same process that is used in rapid prototyping. Rapid manufacturing is used to create functioning end products. Rapid prototyping is particularly interesting for the production of smaller quantities or individualized product. Rapid prototyping, nor rapid tooling, is aimed at producing an end product of high fidelity. The prototypes produce not only looks like end product, but they also function like them. In the rapid prototyping process, design and function can be optimized quickly and easily, providing companies with a wide range of benefits. In addition to rapid production of prototypes, the rapid prototyping technology also includes 3D printing application, CNC machining, and several other manufacturing methods. Why use 3D printer for rapid prototyping? In short, it is fast and relatively cheap. From idea to 3D model to hold a prototype in your hand is a matter of days instead of weeks. Iterations are easier and cheaper to make, and you do not need expensive molds or tools. Brief history of additive manufacturing. 3D printing may seem like a brand new technology, but it has been around for almost 40 years. Now, 3D printers have become much more affordable and user friendly. 3D printing is also becoming much more accessible to the generic public recently. Let us recap and highlight the important milestone and landmark moments that 3D printers have reached, becoming one of the technology that are revolutionizing the world for its many applications in different fields. Dr. Hidekorama from Japan was actually the first documented person to experiment with 3D printing technology back in 1980s. He created a 3D printing system in which a resin is exposed to UV light layer by layer, producing a solid 3D model. Although Dr. Kadama filed for a patent, he never did complete all the requirements for obtaining one. So his 3D printing method was never commercialized. Chuck Hull is often credited as one of the pioneer for 3D printing, as he was the first person to officially file for a patent for SLA 3D printing back in 1984. Hull come up with the word stereolithography SLA, which refers to the model in which objects are made solid by printing out layer of material that are cured by ultraviolet light. Another new 3D printing method also come up around this time called SLS 3D printing. In selective laser sintering or SLS 3D printing, a laser is used to turn loose powder into solid material. In 2006, SLS 3D printing became commercially available. In 1988, Scott Crumb came up with fused deposition modeling FDM 3D printers as he was looking for a simple way to create a toy for his daughter. Surprisingly, FDM 3D printing was created after both SLA and SLS 3D printing, and it is now much commercially used for prototyping. From 1990 onwards, 3D printing started to evolve as companies, startups, scientists, and medical professionals began experimenting with 3D printers and coming up with different ideas and applications. As a result, new bioprinting and scientific applications were created. In 1999, scientists built an artificial scaffold of a human bladder with a 3D printer. Human cells taken from a patient were then put into the scaffold, which was used to grow a functioning bladder and was successfully transplanted into the same medical patient. In 2008, the first 3D printed prosthetic leg was successfully printed and implanted onto a patient, allowing amputee to walk again and regain a sense of wholeness. An artificial heart was produced with a 3D printing and lost wax technique, and now it is part of medicine department Zurich. The team explains the motivation for the project is to develop a better solution for artificial heart organ. Looking towards future advances in this technology, many of the present day innovation are targeted towards metal 3D printing, bio 3D printing, printing engineered materials, and for improved speed and efficiency. 3D printing has taken up many new portfolios in research, manufacturing, medical, aerospace, automotive, and food technologies. Well, most of the production industries are and organizations have continued to exist due to their rapidity in the production process. 3D printing technology not only helped in increasing the pace of various manufacturing process, but also assisted in decreasing the cost of the manufactured products. In terms of research and development, additive manufacturing could offer advantages on forming complex geometry, reducing lead time, reducing cost, engineering redesigns, expected to receive the prototypes faster and cheaper, more trials, iterations, and error corrections, which all leads to better final products in all respects. Traditional manufacturing results in a lot of wastage. This means that 80 to 90 percentage of raw materials are discarded and only 10 to 15 percentage of raw material are used for production of the final product. At the same time, large amount of energy are expended to the process raw material into shape. 3D printing being additive in nature, produced by adding raw material only when needed, this drastically reduces the amount of wastage or waste that manufacturing produces and ties it well with the notion of sustainability. 3D printing began as an idea for accelerating industrial product development through faster prototyping. Here we have the most commonly asked question of all. What is 3D printing? What is slicing? 3D printing is also known as additive manufacturing due to the process of layering it involves. 3D printing can be defined as structuring a three-dimensional object into its physical configuration form, its digital form, from its digital form. 3D printing enables you to produce complex shapes using less material than traditional manufacturing method. All types of 3D printing technology serves the same purpose of printing the object in its 3D shape. The only difference they have is in the layering technique and material that are specific to each type. 3D slicing is the process of breaking down a design into several layers. It simply involves cutting a design in layers. Slicing software takes scans of each layer of model and will tell the printer how to move in order to recreate the layer. Slicers also tell 3D printer where to fill a model. This fill gives the 3D printed object internal lattices and columns that strengthen the object. A slicer generates a G code from STL, which helps in providing instructions to the 3D printer, and these layers are then deposited one by one on each other during the printing process. STL file format is mostly used in 3D printing slicing, and it is also called as standard tessellation language or standard triangulation language. So STL file format is used for describing surface geometry of an object to be printed. A lot of software is available in the market which can be used for 3D slicing, such as Idea Maker, Cura, Slice 3D, and Simplify 3D, etc. Before a detailed preview of these technologies involved in this process of 3D printing, let us look into few basic 3D printing process. How does a 3D printer work? When we call out the problem, we naturally begins to think rapidly. In this phase, no idea is too big, too small, too complicated, or too simple. All solutions should be recorded so that the idea that stand out can be pulled and developed for the prototyping. The process flow of 3D printing starts with a model, a 3D model. First, a virtual design of the object is made. This design will work like a blueprint for the 3D printer to read. The virtual design is made using CAD software, computer aided design softwares. A virtual design can also be made using 3D scanners, which creates a copy of an existing object. Slicing basically means slicing up a 3D model into hundreds or thousands of layers, and it is done with slicing software. When your file is sliced, It is ready for your printer, 3D printer. These files are then feeding into your printer through USB, SD card, or Wi-Fi. Next, you need to insert the filament into the print head through extruder. Start your print. Your sliced file is 3D printed layer by layer. Take out the model from the print bed and finally post-process it. Now your print is ready. Let us see how to turn a simple sketch outline into a 3D shape. Sketch trace can be drawn freehand. You need to define the overall size of the item you will be creating. Once you have your sketch ready, you are ready to start creating your 3D model design. The first thing you will need is a 3D design software. Now you have completed the process of creating a 3D file. We just need to save it in right format for 3D printing. Now we are going to upload the STL file created to the machine as G codes. Start the printer and transfer the STL file to 3D printer through SD card. Simultaneously, load 3D printing material, set the printing parameters, and the printer starts working. After the 3D printer completes its work, take out the object and do the post-processing. The extra supports for the part need to be removed for post-processing. Now your print is ready to use. Yes. Basically, there are 7 main 3D printing process. Within each type of process, there are unique technologies, and for every unique technology, there are many different brands selling similar printers. SLA printing, more commonly known as resin printing, stereolithography or SLA, was the first ever patented 3D printing technology to be developed and commercialized. It falls under the VAT polymerization category of 3D printing technology. It uses a photosensitive resin material that is cured by laser source. The laser cures the resin point by point in a continuous process and forms the entire object. Digital light processing or DLP is a similar technology that uses projected UV light in place of laser, which can result in faster printing. DLP is used to produce a large part and large volume of parts in a single batch. Each layer flash takes exactly the same amount of time regardless of how many parts are in the build, which makes it generally faster than the laser method of SLA. This is a material extrusion type of 3D printing technology, and they are called fused deposition modeling. FDM printers, 3D printers use thermoplastic materials in a filament form that is heated and deposited onto a build platform in a layer by layer form. It pushes a plastic filament through a hot nozzle to squeeze layer into the print surface in a pattern. There are a lot of different materials that you can use with a FDM printer. FDM printer is the most common type of 3D printer and the type most widely used by business and hobbyists. Selective laser sintering or SLS is a powder bed fusion 3D printing technology that uses powdered polymer materials to form solid object. This technology also uses a laser to sinter or melt the powder particle and fuse them to form the entire object. First, a bin of polymer powder is heated to a temporary temperature just below the polymer's melting point. Then a wiper blade deposit a very thin layer of the powder material, typically 0.1 mm thick, onto its build platform. A laser source then begins to scan the surface according to the pattern laid out in the digital form. The laser selectively sinters the powder and solidifies the cross section of the object. The list of 3D printing technologies and process continues to grow as 3D printing is always changing. The 3D printing industries continues to innovate its hardware as well as the material and process to create objects and parts. As the potential application of 3D printing increases, companies are beginning to find ways to create new business model and opportunities with this technology. 3D bioprinting or bio 3D printing is an additive manufacturing process where organic or biological matters such as living cells and nutrients are combined to create natural tissue like three-dimensional structures. Bioprinting is a type of 3D printing that can potentially produce anything from bone tissue and blood vessel to living tissues. It is used for various medical research and applications, including tissue engineering, drug testing and development, innovative regenerative medicine therapies, etc. 3D bioprinting works similar to FDM 3D printing and is in the material extrusion family. 3D bioprinting uses materials discharged from a needle to create layers. These materials, known as bioinks, are and they are mainly composed of living matters such as cell within a carrier. Carrier materials like collagen, gelatin, alginate, or nanocellulose. And these carrier material act as a molecular scaffold for the structure to grow and nutrients to provide living matters. Construction 3D printing is a rapidly growing area of material extrusion because it reduces the need for labor and cut down construction waste. 3D construction printing technology is used today for building homes, architectural features, sculptures, bridges, etc. The technology involves using extremely large scale 3D printers to extrude a building material such as concrete, clay, etc. Through an engineered nozzle head. These machines generally comes either as gantry or a robotic arm systems. In reality, 3D printed food is still in its fancy. Material extrusion is the most common process for food 3D printing, and it is similar to fused deposition modeling. 3D food printing is a new technology that supports product innovation, on-demand production, and customization. The technology enables consumers to eat fresh and healthy dishes, create a new eating experience, and customize food preferences in shape, color, flavor, texture, and nutrition, etc. There is a poll on your screen. The question is, which is the most commonly used 3D printing technique? You can start your poll. So the correct answer is FDM, fused deposition modeling method. How to get a good print quality with 3D printing setting? Getting good print quality with 3D printing settings is possible when experience and knowledge on the 3D printing parameters are acquired. What setting lead to high quality? How can you speed up the 3D printing time? Acquiring knowledge on the different printing parameters can provide more clarity on the influenced parameters, thus enabling a better print experience. Profiles in 3D printing are the set of parameters that defines the machine settings to print a part through the use of slicing software. When varying any of the slicing settings, the results obtained may consequently be different. Since every material and every printer are different, 3D printing setting will need to be adjusted to reach a good print quality. Also, depending on the geometry of the 3D file, sometimes we'll have to fine tune it. One of these important factor is part orientation, and it is also called as build orientation. How you orient your part in the printer will play a significant role in delivering the final quality you want from additive component. By orienting the part in different direction, there is a significant difference in the print quality. For functional parts, it is important to consider the application and the direction of the loads. For example, FDM print parts are much more likely to delaminate and fracture when placed in tension in Z direction compared to XY direction. Infill density is that the fullness of within a part. In slicer, this can be usually defined as percentage between 0 and 100, with 0% making a component hollow and 100% completely solid. As you will be able to imagine, this greatly impact a component's weight. The fuller the inside of a part, the heavier it is. The most important of those parameters fall into two fundamental aspects. They are infill density and infill pattern. For most standard prints that don't have to be strong or super strong, it is recommended to use an infill density of 15 to 50%. The density percentage keeps print time low, conserves your material, and provide good strength. Functional print must be strong, therefore, it is recommended to use a higher infill over 50%. The setting is extremely high, so it will be longer for the print time and consumes more material. Ranging from a simple line to more complex geometry shapes, infill patterns can affect a part's strength, weight, print time, and even its flexibility. There are many different types of 3D printer infill, like linear, honeycomb, grid, triangles, catfill, hexagon, etc. In most cases, an infill density between 20 and 50% is ideal. Less than 20% result in flimsy parts, whereas more than 50% began to take too much of print time and use more material. One crucial aspect of 3D printing that significantly influences the quality and functionality of printed object is the concept of shell. Shells, also known as outer perimeters or counters, refers to the outermost layer of a 3D printed object. Understanding the role of shells is vital for achieving optimal print results and ensure the desired characteristics of the final product. The relationship between shells and infill is interconnected. Shells determine the outer appearance and define the overall shape. The infill provides internal structure and affects the structural integrity of the object. Finding the right balance between shell thickness and infill density is essential for achieving the desired strength, weight, and print time for the given object. So basically, the layer height of is measured in usually in or micron that your nozzle extrudes for each layer of 3D print. It is also known as layer thickness and resolution in 3D printing. One of the most common reason for changing 3D printer layer height setting is to increase print speed. Generally, increasing layer height will decrease the resolution and quality of the print. Layer height can be optimized for each print in order to attain the faster print speed while maintaining a certain amount of resolution. As previously mentioned, layer height affects the speed and overall print time of your object. Layer height affects print time because your print head has to print each layer one by one. A smaller layer height means your object has more layers in total. The impact of layer height is more noticeable on curves and angles, and it is less predominant or prominent on straight vertical walls due to the layer by layer nature of 3D printing. When deciding on a layer height, it is also important to consider whether the part will be post processed. A higher layer height may be a better choice if the print is going to be sanded or acetone smoothened or painted. 3D printing materials can vary widely with options that includes plastics, powders, resins, metals, and carbon fiber. Most consumer 3D printed products are made from thermoplastics. Designers and engineers prefer creating functional prototype from 3D printing material that have the same or similar material properties as what it is used in creating the finished products. Plastics are the most widely adopted 3D printed materials, and it comes in filament, resin, granules, and powder forms. Polylactic acid (PLA) is one of the eco-friendliest option for 3D printers. Polylactic acid is sourced from natural products like sugarcane and cornstarch and is therefore biodegradable. It begins to deform at temperature higher than 60 degrees Celsius and print at 110 degrees Celsius. Acrylonitrile butadiene styrene (ABS) is valued for its strength, durability, robustness, and temperature resistance. It is good for making conceptual and functional models. It is printable at about 220 degrees Celsius with a heated print bed. PETG is a variant of PET that has been combined with glycol. It has high transparency and can be printed at low temperature with increased flow speed, therefore allowing the 3D print faster. Because of its weather resistant, it is often used for outdoor applications. Peak uses FDM or SLS technology for the production of high performance part. Plastics of these types are highly resistant to stress, temperature, and chemical, and they can be even exposed to X-ray and gamma radiations. They are easy to machine and fabricate, but they require a 3D printer capable of reaching 400 degrees Celsius. The temperature is extremely important for making a high fidelity 3D printer with a 3D printer. The chemical makeup of a thermoplastic directly influences its glass transition temperature, the temperature at which the filament turns from brittle filament into a rubbery substance that can be extruded. This temperature needs to be reached for a proper printing, and since each plastics has a different glass transition temperature, every filament needs to be printed at different temperature. Under extrusion occurs when too little filament extruded during a print. This can result in gap, missing layers, insufficient smaller layers, and even little dots or holes appearing in the print. Print quality and the print strength are compromised when under extrusion occur. It can be either issue or related to its setting, print setting, or its calibration. Overextrusion can occur when your printer extrudes too much of material. It leads to dimensional inaccuracy, layer drooping, stringing, oozing, and even clogs to your nozzle. We know that FDM 3D printers works by depositing layer over layer of thermoplastics. Uh, because of that, each new layer must be supported by the layer beneath it. If your model has an overhanging that is not supported by anything below, there is a good chance it will drop or even fall, and you will need to add a 3D printed support structure to ensure a successful print. Getting supports right is therefore a very important aspect of 3D printing complicated structures. Not all overhanging needs to be supported. If an overhanging tilts at an angle less than 45 degree from the vertical, then you may be able to print the overhanging without using support. 3D printing will continue to develop well in the future and have a huge potential. Here is the list of our service we can help you: material selection, new product development, prototyping, product optimization, material testing, characterization, conduct root cause analysis, product sustaining activities. That is all for today. I see that there are few questions coming in. We will respond to them via email. For any further queries, you can contact us. Contact details are on the screen. We would be happy to help you with any of your product design, development, prototyping, optimization, and troubleshootings. Please note a recorded version of this webinar will be available on our website in a week's time from now. We will always also send you an email with the link on your registered email ID to access this webinar. I hope you all found this presentation very informative. Thank you for joining us and dedicating your valuable time to engage with the topics we discussed. We look forward to future opportunities to connect, share knowledge, and grow together with us. Thank you all.